Mr. Taru. In this video, we are going to learn something extremely cool. It's a major branch of calculus. It's called the derivative. And what the derivative is going to do in calculus, along with the tangent line problem, is we're going to be able to combine a very old idea that you've been using and learning and working with way back since pre-algebra, which is slope. But if you combine that old slope, rise over run, with our idea of limits that we just started going through in the first chapter, something really cool happens. It allows you to find the curve, or excuse me, the slope of a curve at any given point. It's called the slope of the tangent line. Now in this video, this is going to be a full, about 9 or 10 example video of anything hopefully that you'll need to get through your first section of learning how to do the derivative with the definition of derivative and the tangent line problem. We're going to be finding the slope of the tangent line at a point. We're going to be finding the equation or the derivative function, the equation that will allow us to find the slope at any given point along the curve. That kind of sounds like I said the same thing, but when you use the definition of a derivative to find the slope of the tangent at a point and you want the slope somewhere else in the curve, you have to go through the whole process again. Whereas if you just find the derivative function, that function will allow you to put in pretty much almost any x value and find the slope at that point. But the definition of derivative starts to have some issues when you have a derivative which is undefined. So we're also going to be taking a look at examples of finding the derivative of a vertical line, trying to find the derivative at a sharp bend. We're going to be talking about the relationship of finding the derivative of a function and continuity at a particular point. There's a relationship there. We'll be looking at that as we try and find the derivative of a floor function or a step function, the greatest integer function. We're also going to be working through examples near the end of the video where I help you find the tangent line to a curve that goes through another point not on the curve itself, and a tangent line which is parallel to a previously or a given tangent line. So we've got a lot to talk about, but first thing I want to do is turn off the air conditioner so you don't hear that in the background and show you how the limit process will allow us to work with 2 points on a curve and find an approximation of the slope of the tangent line. And it'll be pretty darn accurate with this idea of limits. Alright, so what we're looking at here is a curve with 2 points, and I'm going to draw a line through these 2 points. And the slope of this secant line, because it's intersecting at more than 1 point, the slope of that secant line in pre-calculus we would have called the average rate of change. It's supposed to be there to estimate the direction or the slope of this curve at that point. I want to work with finding the slope at that point, not necessarily at this point with the much more complicated coordinates of c plus delta x plus f of c plus delta x. That line, how well do we think this line estimates the slope of this curve at that point? Well, it seems like the line is steeper, that slope would be a greater number than, it kind of looks like the curve is sort of going off in this direction. So that line is an estimate of the slope of this curve at that point, but it's not a really good estimate. So what we're going to do is, with this idea of limits, and I'll summarize this up here with some nice notes in a second that I'll reveal to you, is I want to take this delta x and reduce it. Like if this is a estimation of the slope of this curve at this point, I could get a better estimate if I move that point closer. So maybe instead of having my point here, I'll reduce my delta x, this horizontal distance, by a little bit, and maybe we'll put our point here. Well, if I redraw that new secant line, best I can without a ruler, we can see that the slope of that line is starting to come down a little bit and do a little bit of a better job of estimating the slope of that curve at that point, but it still seems like, you know, a tangent line is ultimately what I'm trying to find, the slope of a tangent line, and a tangent line is only supposed to touch a curve at 1 point. So you still need 2 points to find the slope of a line, but those points aren't really close enough yet to give me a really good estimation. So what we're going to do is, well, I'm just going to move my point even closer and reduce that that delta x, I didn't really show it there, but this is my delta x now compared to my original one. It's smaller. If I reduce that delta x to an even smaller amount and move a point, or move the point even closer, well, now I have a secant line, because I'm still identifying 2 points, but now I have a secant line that has a slope that is much closer to what appears to be the slope of the curve at that point C f of c. Now, what I'm going to step off here and reveal to you is some notes about how we can, remind us of what our old slope formula looks like, move it into function notation, and then introduce these variables here and show you how limits can allow that point, that delta x. I'm going to let that delta x reduce to 0. Remember you're doing just in the last chapter, numerical and graphical limits, and then we learned about the properties of limits to sort of set these things up to allow this delta x to approach some value. Well, we're going to let that value approach 0 and get those points infinitely close and basically get a tangent line to the curve. It's really technically a secant line because we're using 2 points, but the distance between those points, they're going to approach 0, and thus it's basically tangent. Reduce delta x until the points are infinitely close and you have a tangent line instead of a secant line. The slope of the tangent line is the slope of the curve at that point. Now, let's just build up to the formula for a minute instead of just giving it straight to you. We have our old school slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. In more fancy pants type language, that's delta y over delta x, the change in y over the change of x, or as we've always known it, simply rise over run. If you remember from pre-calculus or maybe your Algebra 2 honors class, you might have seen this formula for slope written as f of x sub 2 and f of x sub 1 replacing the y sub 2 minus y sub 1. That was just to get you used to using the function notation, or try to make you get used to the function notation. Also, if you're doing again, the end of your Algebra 2 honors class or pre-calculus, you might have had this formula called average rate of change. It's the slope of these secant lines. It's the average rate of change between 2 points on a curve, and we had to call it average rate of change because the slope of a curve is always changing. Well, why now, again, do I have these specific labels of c, f of c, and c plus delta x, comma, did I just say plus? I meant comma there, and f of c plus delta x? Well, this point is fixed. We're going to basically write a formula. It's called the definition of the tangent, the definition for the slope of the tangent line, basically, and I want to find the slope of this curve at that point. So I want this point to be fixed, and I want this other point to have some identification to it that relates it to this point, so that I can then, of course, reduce that delta x, as I said, reduce it to 0 and move that point closer to this one, getting a more and more and more accurate estimate of the slope, or the slope of the tangent line. So when I replace that generic x sub 2 with c plus delta x, and the x sub 1 with just c, well, now my denominator, instead of being x sub 2 minus x sub 1, is c plus delta x minus c, and the c minus c cancels out and we get delta x. Sorry for the interruption there. So this formula was given in your book not just as a random formula to use to practice your function notation, but as a precursor to what we're about to learn, which is called the definition of the tangent, or the definition of the slope of the tangent line. We're going to take this old school slope formula, introduce limits, and boom! There's our first main concept of this video. Bam! Here it is, the main idea behind this whole video, and the many, many examples yet to follow. Definition of tangent line with slope m. If function f is defined on an open interval containing c, and if the limit exists, this limit here, the limit as delta x approaches 0 of delta y over delta x, or more formally with the difference quotient from pre-calculus, the limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x, that is going to be the slope of the tangent line. Well, then the line passing through c f of c, we're going to call that the point of tangent c, with slope m, or I might put like a little subscript of tan or tangent, is the tangent line to the graph of f at the point of, again, that tangency. Now it does say if this limit exists. You know, we just talked about limits in the previous chapter. We know that, say, you know, maybe this ends up being undefined and just goes to infinity. That's going to end up being, or identifying the slope of a vertical line. We'll be doing examples of that later. The left and right hand limits may not be equal, whether there's a sharp bend or maybe the graph just is got a non-removable discontinuity at this value of c, which we're trying to figure out. Now these first three examples, again, I've posted in an older video. I think it's called Slope of a Tangent Line, Derivative at a Point. I'm going to walk through the first example step by step, and then because you can find these other two examples, you know, explained step by step by step, I'll just reveal them to you with a pause if you'd like to, you know, try and do those problems on your own. But I'll just reveal the solution all at once. We have f of x is equal to 3x plus 5, and I want to find the slope of this function at the point of tangency of 211. Well, c is that value of x, that value along the x-axis in which we're trying to find the slope of the tangent line. So when I say I want to find that, the slope of that tangent line at the point of tangency of 211, I'm telling you that c is equal to 2. So we're going to say that the slope of the tangent line is equal to the limit as delta x approaches 0 of, now, okay, it's f of c plus delta x. So here's my function, and we're going to do 3 times x, which is going to be, again, c plus delta x, so it's going to be 2 plus delta x. Plus 5 minus, these parentheses I'm putting around the first term in my numerator honestly are a little bit unnecessary, but because we have a minus sign here, you better make sure that if you have more than one term in your function, and you're pretty much guaranteed to have that be the case, make sure you wrap that second term in parentheses. You remember to multiply the negative sign through the parentheses and not make a sign error. So minus, well, now let's see, the formula says f of c, so it's going to be this function with 2 plugged in for x. All over delta x. Now, if I try and, we talked about in the previous chapter finding limits both numerically and graphically, and then we got tired of making all those tables and graphs, so we learned some properties of limits and used properties of limits to find limits with direct substitution when possible. Well, I can't take this value of 0 and plug it into my expression because this is going to become undefined. And so when you do the definition of the derivative, a lot of times, unless the limit doesn't exist because of maybe a vertical line, a vertical tangent line, that denominator will cancel out after a little bit of simplification and manipulation of this expression until you actually can take this 0 and plug it into the expression. It's going to look like this. The limit as delta x approaches 0 of, let's see here, well, we distribute this 3, and we got 6 plus 3 delta x plus 5. And then over here, these are all just numerical values, so we can work this out. 3 times 2 is 6, plus 5 is 11. Now that all simplified to just be one term, so I don't need to worry necessarily about distributing that negative sign, but a lot of times you will, especially when we get into finding the derivative function as opposed to just a numerical slope, or numerical slope at a particular point. So that's going to be, again, minus 11 over delta x. Well, 6 plus 5 is 11, and minus 11, so all those constants are going to cancel out. So again, 6 plus 5 is 11, minus 11 is 0. So we're just left with the limit as delta x approaches 0 of 3 delta x over delta x, and these delta x's cancel out, and we end up with the limit of delta x approaching 0 of just a constant of 3. And we know from one of our properties of finding limits that the limit of a constant is going to always be equal to 0. So, or excuse me, not 0, but 3. Had a little brain fart there for a second. Like, no matter what delta x is approaching, the function's value is 3. It's 3. It's always going to be equal to 3. And that makes sense because look at our original function. It's a line. It's y equals mx plus b. This is a line. It's a linear function. The slope is the same everywhere. No matter what the value of x is, no matter where you go along that line, you are going to have a slope equal to 3. So this question, showing the process of working through the definition of the derivative, it's obvious that it works because we got 3 and we could see that slope in the original function. But this original function isn't a curve. And the cool thing about this definition of a derivative, or the definition of tangent line with slope m, I'm just going to call it the definition of a derivative, is you can find the slope of a curve at any point. So, let's get this erased. I'll put up the previous question, and let's get to it right now. For our next example, we got 2x squared minus 3x plus 1. We're going to find the slope of this parabola at 2, 3. This question is going to work just like the last one, but you know, we'll have a little bit of algebra work that's necessary because we have 3 terms, and especially since one of them is squared. So I'll get us started, and I'm going to walk off. Give you about 5 seconds if you'd like to pause the video and try and finish it on your own before I reveal the answer. And if I feel like there's any important points, point them out and then get on to the next example. So we want to find, again, the slope of the tangent line at this point. So it's going to be the slope of the tangent line is going to be equal to the limit as delta x approaches 0. And again, I want to take this function and plug in c, which is the x-coordinate at the point of tangent c that we want to find the slope at, plus delta x. So it's going to be 2, I don't need those parentheses there, 2 times c, which is 2, plus delta x squared, minus 3 times 2 plus delta x, not squared this time, it's just x minus 1, or excuse me, plus 1. Minus, now I better, with these 3 terms, well, again, I'm always going to be in the practice of using the minus with parentheses, but we are going to plug in a constant value of 2, so this will all work out to a single number like before. We've got 2 times 2 squared, minus 3 times 2, plus 1, all over, again, delta x. Now, these are pretty long questions when you use the definition of the derivative to find the slope of a tangent line at a point or to find the actual derivative function itself. They're long and tedious problems with a lot of algebra. It's a really good review of all your algebra skills that hopefully you remember from last year, and if not, you get a good chance to remember them. But they're long and tedious, and in plenty of places to make some small mistakes that if you show your work, just do one algebraic step in every step and just keep writing step after step after step. Don't try and do too much in your head. You'll make fewer mistakes that way, and if you do make a mistake, like a sign error or something like that, it'll be easier to find and easier to fix, a lot less time consuming. So don't shortcut on showing your work for these problems. It will help you tremendously to get these right more consistently. So I'm going to step off a few seconds. If you'd like to try this on your own, pause the videos, or the video. Otherwise, the answer is coming up just in a few seconds. Well, there you go. I hope you got the right answer. And I can't help but talk about this just a tiny bit. Make sure that you be careful when you take those binomials and you square them. You actually get 3 terms. Don't try and do it in your head and forget the middle term and only get 2. Really common mistake for my students in pre-calculus until I hammer it in to them enough. This is a parabola. It's smooth and continuous everywhere within its domain. So the limit does exist at 2, 3. And so once again, you'll notice that as we simplify our work, that denominator of delta x does eventually get canceled with a factor of delta x that we can bring out of all of our terms in the numerator, and thus allow us to just take that value of 0 that delta x is approaching and get that slope of 5. I've also displayed the picture of the parabola here, roughly, and the point of tangent C in this purple line is that tangent line which we just found the slope of, which is 5. Now, if you're being asked to find something more than just the slope at this particular point of 2, 3, but actually find the equation of the tangent line, well, you've been finding you've been finding equations of lines since, you know, what, pre-algebra or maybe algebra 1. You have a point right here, a point of 2, 3. You have a slope of 5, so you can just plug into your point slope form. And there's more than one way to write the equation of a line, but if you use point slope form, it's y minus the y of your point of tangency. Your slope, which you just found, which was 5, times x minus x. The x coordinate of your point of tangency, or what we used as c. We get y minus 3 is equal to 5x minus 10. Add 3 to both sides, and we get y is equal to 5x minus 7 when you add 3 to both sides. And that is the equation of this tangent line. Okay, I got one more example. This one's going to be the most complicated of the three that we're doing right now, where we can actually find the limit exists at c and such not, and we're just finding the slope again at a particular point. Coming right up. F of x is equal to the square root of x minus 1 at 5, 2. We're going to find the slope of that curve at that particular point. We're going to do that again with the definition of the derivative. So we're going to say the slope of our tangent line is equal to the limit as delta x approaches 0 of the square root of c plus delta x, so the square root of 5 plus delta x minus 1 minus, okay, now we're going to do f of c, so we're going to take the 5 and plug it in, so minus the square root of 5 minus 1. I don't need to use parentheses again because the square root is actually going to act as a grouping symbol as well, over delta x. That's going to simplify to be 5 minus 1, which is 4, and the square root of 4 is 2, so that's going to simplify to be the limit as delta x approaches 0 of the square root of 5 minus 1, which is 4, minus 2 over delta x. I said I was just going to reveal the solution and let you refer to those other videos since some of these examples are repeats, but if this is the only video you watch, you're not going to want to maybe necessarily go find another one. So I'm going to go ahead and talk through this. Hopefully you remember this a little bit as you started finding your limits with properties of limits, and we can manipulate this, and if not, let's take a look at it. We can manipulate this expression so that we can actually take the value of 0 and plug it in, because right now, of course, we're going to be trying to divide by 0, and that makes this expression undefined. And so the only other way, if I can't manipulate this to get that denominator to not be such that I can, that would prevent me from plugging in 0, I would have to resort to either doing, finding this limit either graphically or with those tedious tables that we did and finding limits numerically and graphically. So really hope we can manipulate this so I can just plug in the 0. And what we're going to do is we're going to rationalize the numerator. So we're going to multiply the numerator and denominator by the conjugate, so it's going to be the square root of 4 plus delta x plus 2 again, numerator and denominator. This is a difference of squares pattern. It's a minus b times a plus b. That's the factored form of a difference of squares. So when I distribute these together, my middle term is going to cancel out, but I'm going to go ahead and show it to you. To kind of speed this up a little bit, I'm just going to pause between the steps. That was a lot quicker than watching me write it. I've taken my two binomials and distributed them together, and of course, again, pointing out that difference of squares pattern, these two middle terms are going to cancel out. We're also going to have 4 minus 4, of course, is 0, so those are going to cancel out. And I have left my denominator in factored form, if you will. I haven't distributed the delta x because the whole goal is to get that delta x to cancel out so I can plug in the value of 0. and get this limit with direct substitution. Well, if all of this cancels out, I'm just left with delta x, and that one sole remaining term can be divided with itself in the denominator. And remember, this numerator is, we're not adding and getting 0, we're dividing and getting the answer of 1 now. So our numerator is still going to be 1, it doesn't just disappear. Let's get that up here. Now we can take and plug in our value, our delta value, let it approach 0, just do a direct substitution. It will not come out to be undefined, and thus we'll have the slope of this curve at that point. And that is going to be 1 over, I'm not going to write the limit notation anymore because I'm plugging in 0, over the square root of 4 plus 0 plus 2, and that comes out to be, let's just finish that up, 1 over the square root of 4 is 2, 2 plus 2 is 4, and that is the slope, again, of my tangent line. Let's keep my notation neat and do like little m sub t, so I know it's the slope of the tangent line. Now, this is all fine and dandy, but, let me do one more example before I get into actually finding the derivative function. What happens when you try and find the slope of a smooth, continuous curve, but where you're trying to find the slope of that smooth and continuous curve at, keyword on smooth, what happens if the vertical, if the tangent line is vertical? That means that we're going to have some issue trying to get rid of that delta x in the denominator, and so we need to recognize that. It's coming up right now. Now, what's going to happen again with that vertical tangent line? Well, don't forget the equation of a vertical line, which, by the way, is x equals a number as far as the equation goes. Vertical lines have a slope which are undefined, so of course the limit as delta x approaches 0 of our definition here, f of c plus delta x minus f of c over delta x is going to come out to be infinity or negative infinity. So thus, that's why the last section of the previous chapter was about infinite limits. We're going to say, you know, like, the limit really doesn't exist. We might say that it's infinity or negative infinity, but we're actually, by stating that, we're stating that the real limit doesn't exist. Thus, the slope of our tangent line is undefined. So over here, we're just plugging along, we're doing our homework, find the slope of a tangent line through 0, 0 for f of x, which is equal to x to the 1/5. So the slope here is equal to the limit as delta x approaches 0, and we say, well, okay, so it's c, or c, excuse me, I should be looking up here, c plus delta c, so, or excuse me, c plus delta x to the 1/5 power minus f of c, or 0 to the 1/5 power, all over delta x. Okay, so everything seems good so far. Then we get the limit as delta x approaches 0 of, oh, well that's just 0, and 0 plus delta x is just going to be delta x to the 1/5 power. So we end up with delta x to the 1/5 power over delta x. Even though this is a bit of a different looking base than maybe you would have had in Algebra 2 Honors or Pre-Calculus, it's still a base. When you divide like bases, you take the exponents and you subtract them. So we have, this is equal to, just come off to the side here if you need to, we have delta x to the 1/5 minus this exponent of 1. But we need common denominators, so that 1's going to become 5 over 5. And that, of course, is delta x to the negative 4/5. So I could say that this is equal to delta x to the negative 4/5, or just write it in such a way I don't have that negative exponent, which means it's going to be the limit as delta x approaches 0 of 1 over x, or delta x, excuse me, to the 4/5. And really nothing else can be done to that expression. Yet I need to let x approach 0. if there's no way for me to manipulate this into an expression or a function that agrees to with this one all but one point at c, then I'm left trying to find this limit by either doing a graphical approach or a numerical approach. So instead of just doing a long t-table like we did initially when finding limits numerically, I just want to kind of think about this a little bit. If I let x approach 0 from the left, of 1 over delta x to the 4/5 power. Let's not forget that the top number is a power and the bottom number is a root. So if I take a number that's less than 0, because I'm approaching from the left, like just a negative number, and I take a negative number and I do an odd root to it, it's still going to be negative. But then I'm taking that negative number and raising it to an even power. Well, a negative number raised to any even power is always going to come out to be positive. And as this becomes closer and closer and closer to 0, 1 divided by an infinitely small number because it becomes infinitely large. So this is going to approach positive infinity. And if I do the right-hand limit, delta x to the 4/5. Well, if I plug in a positive number, I take the 5th root, I get a positive answer. I take that positive answer and I raise it to the 4th power. It's still positive. I still have 1 being placed over and infinitely, now we're approaching 0, so again the denominator is becoming infinitely small, approaching 0. That's going to make the overall fraction become, or approach again, positive infinity. So this limit, I can say this, this is a definitive limit. The left, well, I can say the infinite limit is infinity because the left and right limits are both equal, but I'm actually validating that, there is no real limit, that the real limit doesn't exist. Thus, we have evidence of a vertical tangent line. Let me just pause, I want to give you the visual or the graph of this function that we're looking at, and also the graph of the original function and the, basically what we have here is 1 over x, like a derivative here, and compare the two. So what I've done is I have drawn here in purple roughly what the function f of x is equal to x to the 1/5 looks like. It's a smooth continuous function. But there is that sharp rise at x equals 0, and there's that vertical, well, it's actually kind of like the y-axis, but our vertical line, which is our tangent line at x equals 0. And in orange, even though I'm saying sort of like the definition of the slope of the tangent line interchangeable with the definition of the derivative, it's not exactly correct. So I'm getting ahead of myself here a little bit because of all these concepts I'm trying to lace together for you. But f prime of x, or the derivative of x, is equal to 1 over x to the 4/5. I'm kind of just taking this delta x here. We're still trying to find the derivative at a point, but we can see that there's some kind of variable here to the 4/5 in the denominator. And I wanted to show you how it approaches infinity, or it approaches infinity as you approach at the x value of 0 from the left and the x value of 0 from the right. Thus the two-sided limit is the same, just happens to be infinity, which is nice to say that it's equal to infinity, but we're actually validating that the real limit does not exist. Thus the slope of the tangent line is undefined, or that the tangent line is vertical because we had that limit of either infinity or negative infinity. We also have a couple of other special cases where we might try and find, or we're going to try and find the derivative at a sharp bend. You can't find the derivative there as well. And also finding the derivative of a function when it's sort of like a step function or discontinuous in the sense that it's non-removable, where the left limit and right-hand limit are not equal. I'm trying to decide if I want to do those. Yeah, I think I will. I'll do those two other special cases before we get into actually using the full-blown proper definition of a derivative, which means we're going to be finding the derivative function as opposed to just the slope at a specific point. Derivative at a sharp bend. Remember those absolute value functions? Inside the absolute value function, where that expression is able to equal 0, and the function without the absolute value symbols would sort of cross through having positive y values into negative y values or vice versa, Well, the absolute value function tells you how far a value is away from 0 on the number line, basically thus letting us sort of see that it just cancels out the negatives. So we get these sharp bends, like as soon as it hits where it should be hitting the x-axis, unless there's a vertical shift, it's going to sort of bounce right off of it and make a sharp bend at that one particular value of x. Well, that value of x is going to be -3 here, because if I plug in -3, I get 0 inside my absolute value function. So we're going to try and find the slope of that function, which is again going to be continuous along its entire domain. Find the derivative at that point of x equals -3, or the c equals -3. So we're going to say the limit, or the slope of the tangent line, is equal to the limit as delta x approaches 0 of, and we're going to let this equals again c, and so it's going to be the absolute value of -3 plus delta x plus 3 minus, and we're going to take that value of c and plug it in, so minus the absolute value of -3 plus 3, did I just call that +3? It's -3 of course, over delta x. Okay, and maybe we're not really even thinking about that sharp bend showing up. We're just, going through all these definition of derivative or definition of the slope of a tangent line formula over and over again, and this happens. We have the limit as delta x approaches 0 of, well, let's see here. We have -3 plus 3 is 0. Those cancel out. And so we have the absolute value of delta x over oh, well, this is 0 again. All of a sudden, this is becoming what looks like, being extremely simple. And we again have a situation where we have a denominator, this delta x in the denominator, and not having any way of canceling it out. So again, we can find the limit both numerically with a table of values like we did before, or just sort of think about it like I'm going to do, or with a graph. We're going to be thinking about just, what's happening with the signs here. If I want to find the limit as we approach, or if we let the delta x approach 0 from the left of this function, and think about what the absolute value function does. I mean, we have the exact same expression just sitting alone in the denominator and sitting in the numerator. And if we remember that, again, the absolute value symbol just sort of makes the negatives disappear, if you will, after you simplify what's inside, we can kind of see that it's delta x divided by delta x. So if we want to approach, and which comes out to be some form of 1, so if we approach 0 from the left, that means we're plugging in negative numbers. So if I plug in a negative number into this numerator, the absolute value symbol is going to make it positive. So we're going to have a positive value up here. I guess we could say, if we want to approach from the left, you could maybe plug in like a negative 0.1 and a positive 0.1. Maybe we should just do that. Do like a test number. Let's go ahead and plug in negative 0.1, because that's kind of close to 0 and to the left. Plug in a negative 0.1 in the denominator, and the absolute value is going to make that positive. And that's going to come out to be -1. Okay, well that's fine, as long as the right-hand limit is equal to the same, then the two-sided limit exists. So the limit as delta x approaches 0 from the right, well, you can think about it, since this is going to cancel, going to be 1, or you can, use an actual test value. I'm going to go just to the right of point of 0 and use positive 0.1. Well, the absolute value of that positive 0.1 is going to keep it as 0.1. And that is equal to 1. So, we know, of course, that for a limit to exist, for the limit as delta x approaches 0 to exist for this expression or function, that the left and right hand limits would have to be the same, and they're not. So thus, the limit, which is we're trying to find the slope of the tangent line, doesn't exist. We can't find the slope of a function. We can't find the limit as x approaches 0. We can't find the slope of that tangent line at that sharp bend, in this case where it's equal to -3. We're also not going to be able to find the derivative function is going to be undefined also at that point since we can't find the limit. So, can't find the derivative, you can't find the slope of a tangent line at a sharp bend because the left and right hand limits, they're not equal. Sorry, keep now using this word of differentiability and differential, or derivative, excuse me, but I just thought the video would flow better if I did all these special cases trying to find the slope of the tangent line at a specific point before I got into the proper definition of derivative, which is very, very similar. Again here, this was the second example with the vertical tangent line example I just did, and this one here at the sharp bend, that again, f is continuous at C, but not differentiable at C, or in other words, we can't find a real slope of the tangent line. However, if f is differentiable at C, then f is continuous at C, or in other words, differentiability implies continuity. Now we'll get to that proper definition of finding derivative here in just after one more example. So if you can find the derivative at a function, if you can find the real slope of the tangent line at a point, and the function is continuous at that point. But we've seen that just because it's continuous doesn't mean that we can find the derivative or the slope of the tangent line at that point. I got one more example. This one is going to be a floor function, or the greatest integer function. Just to finish up our last final special case before we get into actually the proper definition of derivative and finding derivative functions as opposed to just slopes at a given point. Now, this is the coolest part about this section. Amongst all these other examples I'm giving you, of course, you can do your homework. Here we're going to take the difference quotient, we're going to take out the value of C and replace it with x. So instead of finding the slope at one fixed point on a curve, that's fine, but if I find the slope at x equals 2 and I want to find the slope at x equals 4, I got to go through this whole limit process again, and you can see it's not very quick. So if we replace that x with a c, that means we're going to do the same process but in general terms as opposed to just at one specific value of c. What that's going to do for us is find a derivative, and this is the definition of the derivative. I was actually incorrectly saying definition of derivative when we were actually using the definition of a slope of a tangent line at a point. This is much more powerful in the sense that when I do this process, I get something called f prime of x, or the derivative of f. It's going to be, well, let's see. It's going to be another function in terms of x, that function is going to tell us the slope of the original function at any point. So when I walk through this limit process one time, or just the original time, we get this new function, this derivative function. Then if I want to find the slope of the original f of x at 2, and then at 4, all I have to do is plug 2 into this function. I get the slope of the original f of x. Plug 4 into this function, assuming that the limit exists, and I'll have my second slope. So I can find the slope at any point along this curve I like, as long as this limit exists at that point. So this is for all x in which the limit exists, f prime is a function of x. F prime is gives the slope of the tangent line to the graph of f of x, as long as f of x has a tangent line at that point. We already talked about how difficult it is, or the issues we can have with vertical tangent lines having this limit be undefined, or actually equal to infinity or negative infinity, and we try to find the slope at a sharp bend. So we don't, you know, we can't always find the slope of a curve at any point, but almost all of them. So differentiation is the process called finding the derivative. So I'm calling this f prime of x, but I can also say this is the derivative of f of x. A function is differentiable at x if its derivative exists at x, and we've had a couple of examples already where we had an issue with that, like I just said. It is differentiable on the open interval of ab if it is differentiable at every single point along that open interval of ab. F prime of x, as you can hear, I'm reading f prime of x, is f prime of x, or the derivative of y with respect to x. These are kind of interchangeable. A lot of times, just to ease the notation and just to kind of write a little bit of shorthand, we call that y prime of x, y prime, or d over dx of f of x. And then we have this notation, which honestly I don't use in my, I'm not going to use in my notes, but my textbook mentions it, d of x, or d subs, well, d of x, or it's really kind of a subscript, dx of y. See, I'm even positive how to say that because I don't really use that notation. This is, again, read derivative of y with respect to x, and this d over dx, this is like the process of, I'm going to find the derivative with respect to x of my function f of x. Finding the derivative of f of x with respect to x. Now we can also find, you know, with respect to t, a lot of times if we're doing some kind of time plot, or if we're doing some kind of problem that has a function in terms of time, we can find the derivative in terms of time and all kinds of things. But of course we're just getting started with derivatives, so how about we just keep it with respect to x. Now I got two more examples. I know we're already at 40 minutes, so thank you for sticking along. I'm also going to, at the end of this video, be doing again that greatest integer function where the function is discontinuous at some point which we'd like to find the derivative of, or attempt to show you that you actually can't because it's not continuous. And then we're going to be finding the equation of a tangent line that is parallel to a given line, and also find the equation of a tangent line through a point that goes through a point that's not actually on the curve. And hopefully this one video helps you get through your homework, probably at the beginning of learning again, of course, about your derivatives. With that definition, find the derivative by the limit process. We have f of x is equal to 2x squared minus 3x plus 1. This is a parabola. We know parabolas to be smooth and continuous along their entire, through the entire domain of all real numbers. So no problem with this having any issues with being able to find the derivative. It's going to be differentiable among the all real numbers of negative infinity to positive infinity. So f prime of x, or the derivative of x, is going to be equal to the limit as delta x approaches 0. Now remember, we're not plugging in c plus delta x, we're plugging in x plus delta x. It's going to be in general terms. So 2 times x plus delta x squared minus 3 times x plus delta x plus 1 minus, now that we're actually going to find the derivative, sort of like the general form of the slope, we're not going to be plugging in a value of c, which just gives us a constant for this polynomial. That means here's really where I was trying to emphasize it's important for you to, with that minus sign and subtracting here, to use parentheses to remember. So let me just write this out here first. 2x squared minus 3x plus 1. That you remember to wrap that function in parentheses so that you have to carry that negative sign through through the multiplication, and that way you don't make any sign errors. The rest of this problem is going to be extremely similar in the mathematical steps of my previous example. So I'm going to step off, and you might want to pause the video and try and finish this algebra yourself and see what the derivative is. I'm not going to walk through this step by step because of all the examples I've already done. The algebra is the same, just a lot more variables because this doesn't end up coming out to be a constant value. And of course we don't have some constants in here as well. So just be more careful with your algebra, do it one step at a time. Don't try too many things at once or anything in your head, so that if you do make a small mistake you can find it and go back and correct your work. Alrighty then, here's all the algebra. Rest assured, by the way, in the upcoming sections we are going to learn a quicker way of finding these derivatives. You might also, as you go through these couple of examples, look at your original function in your homework and your derivative and start seeing if you notice a relationship between the two, and that might give you a heads up on how we're going to be approaching these derivatives in the upcoming sections. Keep a note of this derivative, the slope of this function. I'm going to be using that in my last two examples in this video. Alright, I got another one coming up. It's a fraction and involves radicals. So guess what? It'll be kind of hard. We'll make it easy. Same directions. Find the derivative by the limit process. So, f prime of x, or the derivative of f, is equal to the limit as delta x approaches 0. Now remember, we're plugging in, again, x plus delta x, so we have 2 over the square root of x plus delta x minus 2 over the square root of x all over delta x. So we're going to have quite a bit of work finding common denominators and working with fractions, which we all know we love to do. So we're going to find a common denominator. We're going to do that by multiplying the first fraction by square root of x in the numerator and denominator, and the second one by the square root of x plus delta x. And to not have you force you to watch me write, just make it appear. Well, you have a fraction divided by a fraction, so hopefully you remember that when you divide fractions, you actually need to multiply by the reciprocal of the second fraction. That second fraction is the denominator. So we're going to take this delta x in the denominator and move it up with multiplication and have 1 over the delta x. Now, don't worry about taking all these factors in the denominator and multiplying them together, because remember, we're trying to get that delta x to go away so I can plug in 0. If I can make it go away. So we have a binomial in the numerator with 2x, 2 square root of x minus 2 square root of x plus delta x. And just like we learned and should have been practicing when you learned about finding limits with properties of limits, and even early in the video, we want to multiply the numerator and denominator by the conjugate of this binomial to get these square roots to cancel out, and hopefully, well, that's not the main purpose, of course, but hopefully is to manipulate this again so we can let that delta x go to 0 by getting it to cancel with something in the numerator. So let's see what happens. So we've multiplied by that conjugate, which of course is that a minus b times a plus b pattern, the difference of squares pattern when you're factoring. So I know I'm not going to have that middle term. Usually you get a trinomial, right, when you multiply two binomials. So we have 2 times 2, which is 4, and the square roots cancel out on the x. Same thing happens over here. Negative 2 times positive 2 is negative 4 times, again, that radical cancels out, and we get x plus delta x. Now, don't forget to wrap that in parentheses, because square root symbols are not only a math function, but it's an actual grouping symbol as well. So if you don't wrap that x plus delta x in parentheses, you'll forget to take this negative 4 and distribute it through the parentheses and have sign errors and probably think that that delta x does not actually cancel out, which it will. So we have 4x minus 4x is equal to, of course, 0. And now that we have only one term in the numerator, negative 4 delta x, and that delta x now is a factor, not just part of a term, we can cancel out this delta x from the negative 4, leaving negative 4 as my numerator right there. That looks kind of confusing. It looks like it might be negative 8. So let's just circle that lone remaining negative 4. Now I can take, with that delta x factor out of my denominator, take that 0, plug it in, and a lot of nice stuff's going to happen, and we'll be done. F prime of x is equal to negative 4 over, now let's not forget we're plugging in 0, right? We're letting the delta x approach 0, so this is going to approach 0. This delta x is going to approach 0, and we have the square root of x times, well now this is going to be just simply square root of x, so square root of x times square root of x is x. We've got 2 square root of x plus 2 times, oh well, I'm adding by 0, so that's kind of basically just 2 square root of x again, and 2 square root of x plus 2 square root of x is 4 square root of x. Now again, my numerator and denominator have one more factor that can cancel out. That's that common factor of 4, and my final answer is the derivative of f, or f prime of x, is equal to negative 1 over x square root of x. Okay, let's take a look at trying to find derivatives, the derivative with that greatest integer function, and then do those last two examples. So now we're going to take a look at trying to find the derivative at a point in which the function is not continuous. What happens? Well, it turns out to be not differentiable. If f is not continuous at c, so we're going back to that finding the derivative at a point instead of just the derivative function, it is also not differentiable at x equals c. In our example, we're going to use the greatest integer function, which again gives us values of n such that n is going to be less than or equal to x. Now, to work through this example with these tables, I'm going to use an alternative form of the derivative, which is f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. It kind of looks like your, well, it doesn't look exactly like your average rate of change formula from pre-calculus. But again, the limit process is going to allow the value of x to approach c, thus taking this point and pushing it closer and closer and closer to our original set point we want to find the slope at, which is c f of c, and thus still giving us the slope of the tangent. Well, what happens? Now it looks like, if I look at this graph here, this line's horizontal, so it seems like the derivative, remember the derivative is slope, so our slope here is 0, and slope here seems to be 0 and 0 and 0, but obviously at the value of 1, 2, or 3, and we're going to let c equal 1, by the way, and try and find the derivative at x equals 1 after I get that phone. Oh, it's already been picked up. We have to jump from a y value of 0 to a y value of 1, so clearly something's happening there, and we're going to have an issue trying to find the derivative. This is no easy way to get rid of the x minus 1 in the denominator, so we're going to find the left and right limit using tables, just like we did in the first start of learning about limits and finding them numerically and graphically. We're going to let x equal 0.9. Well, if I plug 0.9 into my greatest integer function, it's going to give me 0, and 0 minus 1 is negative 1 over 0.9 minus 1. Well, you end up simplifying that, you get a value of 10. Move a little closer to 1 from the left, you get an answer of 100. Move a little closer, you get to 1,000. If you move a little closer, you're going to approach a slope or a left limit of this derivative function, which is infinity. So yeah, as you approach 1 from the left, the slope effect, is going to have to kind of like go to infinity to get up here to the next step of our greatest integer function. Now as you approach to the right, now we've already shown, even with that one-sided limit, that it is infinity, and now we talked about infinite limits, but even stating that the limit is infinity is stating that the real limit does not exist. As you approach from the right, and we say let's take 1.001 and plug it in here and see what the value is. Well, 1.001 plugged into the greatest integer function brings it down to just 1, and 1 minus 1 is equal to 0. Plug in 1.01. 1.01 plugged into our greatest integer function comes out to be 1. 1 minus 1 again is equal to 0 over something, but if the numerator is equal to 0, then all of these values are going to be 0. So as I approach 1 from the right, this limit is equal to 0, which also, remember, you might glance at this and go, well, I'm approaching 1 from the right. The limit of this function as I come into the right, from the right of 1, is equal to 1. But remember, we're trying to find the derivative, which is slope. And this is a horizontal line. And it kind of makes sense then that this horizontal line would have a slope equal to 0. But again, on the left-hand side, approaching 1 with that undefined value, and then you got to step up to the next step of our greatest integer function. The left and right limits don't match, therefore the limit does not exist, and therefore nor does the derivative, and the function is not differentiable at that point of c, where the function is not continuous. Bam! Find the equation, look you up, of the tangent line to the graph of f of x is equal to 2x squared minus 3x plus 1. Find the, that is parallel to y minus x minus 7 equals 0. So, I want to find the slope of a line that's parallel to that line. You've been doing that since Algebra 1. You need a point and you need a slope. Well, let's see here. What's the slope of the given line? Well, if I take this and I solve it for y, I get y is equal to x plus 7. So the line that I'm given has a slope of 1. I want to have a again, a parallel line, so I want to use that slope of 1. Okay, well, what's the slope of the function? Because this is a parabola, and it's, of course, now that we know, constantly curving, and we can find that slope. Where is the slope of this parabola equal to 1? Well, I'm not going to be able to find that. Well, I could do the, definition of the slope of a tangent line at a point, but I could just write that derivative down, like I said, we were going to use in a previous example, the derivative of f of x is equal to 4x minus 3. Now, if I know the derivative of this function, and the derivative gives me the slope of this function, you know, at any point where the limit exists, or the derivative exists, the function exists, then I can just say, okay, well, I need to have a slope of 1. I need my derivative, my slope of that parabola to equal 1. So 1 is equal to 4x minus 3. And when I solve that for x, I'm going to add both sides by 3 and get 4 is equal to 4x. Divide both sides by 4 and get 1 equals x. Well, again, you need a point and a slope to write the equation of a line. I've got that slope once again, but now I've only got half of the point. So I need to take that value of x equals 1 and plug it back into not the derivative, which is going to give us a slope, but back into the original function. So I know the point of tangency between this parabola and the tangent line I'm about to find the equation of. So the point of tangency is f of 1 is equal to 2 times 1 squared minus 3 times 1 plus 1. That's going to come out to be 2 times 1 squared is 1. 1 minus 3 is negative 2. 2 minus 3 is equal to negative 1 plus 1 is equal to 0. So my point of tangency is 1, 0. Now I have a point and I have a slope, and obviously I've made these numbers to work out rather nicely. The tangent line is equal to y minus the y of my point of tangency, which is, I'm using the point slope form, y minus 0 is equal to 1 times x minus the x of my tangency point, and that works out to be y is equal to x minus 1. Let me just double check. Yes! Alright, if you're still watching, thank you very much. You got one more example, and we'll be done. Woo! Now our last example in the video is going to be probably the one that requires the most thought from you to figure out how to do these problems. Find the equation of a tangent line to f of x, again our common parabola here, I just got done using the derivative of as well. I want a tangent line that touches, of course, is tangent to that parabola and goes through this point. Now we have a parabola. I just did a quick sketch of what's going on. We have this point of 3, 8 over here to the right in space, and we're going to end up having two tangent lines that will go through that point and touch the parabola in only one point, the point of tangency. So of course we need a point and a slope to find the equations of lines. So let's start off with slope. The slope of the function is again, of course, the derivative, and f prime of x is equal to 4x minus 3. Okay, well, I need another way of looking at the slope so I can incorporate this point, of course, and get two answers. We have a y and an x, and that's just not enough. So I need another way of writing slope. This is the slope of the parabola that's constantly changing, but between that point of tangency and this coordinate that's out in space, like I haven't used the 3, 8 somehow, I need to write a slope formula for any point on the function and this exterior point, if you will, that's not on the parabola itself, again, of 3, 8. So slope, we know, is equal to y2 minus y1 over x2 minus y1. Well, I'm going to let this point here, this 3, 8, be my x sub 1 and my y sub 1. And so I'm going to put a 3, excuse me, that's supposed to be an x. I'm going to put a 3 here and an 8 there, but I need a better way of writing the y sub 2 and the x sub 2. So the y, how do we find the y? Where is that going to come from? Well, it's a y coordinate that's on this parabola. And how do you find y values? Like graphing with t-tables. You plugged in an x and found a y. So I'm going to rewrite this, replacing y sub 2 with, and you might have it written as f of x, with this function. Okay? Alright, I have two ways of looking at slope now. I've got the derivative, which is 4x minus 3, and I have a slope formula that actually incorporates the value of 3, 8 right here. Now what I want to do is put these together so I can solve for x and find our points, or at least the x coordinates for our 2 points of tangency, which means I'm going to take out the m. I'm just doing the substitution method basically to solve a system of equations like you did at the end of Algebra 1 and Algebra 2. So the 4x minus 3 goes here. We're going to work this out. We're going to multiply both sides of our equation. Let's just wrap that up in a big old parentheses with x minus 3. It's going to cancel out that denominator. And when we distribute these together, we're going to get 4x squared minus 3x minus 12x. Negative 3 times negative 3 is positive 9. That's going to be 4x squared minus 15x plus 9 is equal to, over here, of course this has a power of 2, a power of 1, and we got 1 minus 8, which is going to be negative 7. We have a quadratic here coming up. We're going to have to get the set equal to 0, so I'm going to bring the negative 2x over with subtraction. We're going to bring the negative 3 over with addition, and we're of course going to bring the 7 over with addition as well, doing the opposite math operations, and we get 2x squared minus 12x plus 16 is equal to 0. We're going to solve this for x, and we're going to take the 2 out first. This is a factorable trinomial. We're looking for factors of 8 that add to negative 6, and that's going to be negative 4 and negative 2. So our points of tangency are equal to 4 and x equals 2. Well, I'm going to repeat this kind of like the same thing now as I finish my last problem. I have a, I will have a slope. But first thing I need to do is look at these points of tangency. I need my 2 points of tangencies that come from having an x-coordinate of 4 and an x-coordinate 2. So I'm going to get this board erased, do a little bit of labeling, I'll be right back. So I went ahead and marked the graph. I found our points of tangency by taking our 2 values of 2 and 4 and plugging them back into our original function. So now we've got 2 points. That means we're going to have those two tangent lines again. And we have slope. Now I didn't write the slope out yet for each of these lines, but the derivative is going to tell us the slope at the x-coordinate of 2 and at the x-coordinate of 4 as I work out these problems instantaneously. So we got y minus, I'm going to use point slope form, so y minus the y of our point, which is 3, is equal to m. Okay, well that's going to tell us what it is. So 4 times our x-coordinate is equal to 2. Minus 3, so that's our y equals, or y minus y sub 1 is equal to m times x minus x sub 1. 4 times 2 is 8, and 8 minus 3 is 5. Take the 5 and distribute it through the parentheses, and we get y minus 3 is equal to 5x minus 10. Add both sides by 3, and one of our tangent lines is y equals 5x minus 7, because negative 10 plus 3 is equal to negative 7. The other tangent line is going to be y minus the y coordinate, which is 21, is equal to 4 times the x coordinate. We're finding the slope of the function at 4, so again 4 times 4 minus 3 times x minus the x-coordinate here of 4. And of course, with the same process of simplifying this algebra, we are going to get a, let me just double check my work here. Yes, we are going to get a final answer of y is equal to 13x minus 31. If you got through this very long video, thank you very much. I hope this matches the problems that are in your textbook where you're dealing with the definition of the derivative and the tangent line problem. I'm Mr. True, and I'm finally out of here. Bam! Go do your homework.